My name is Sophie Swinkels. I work for Nutritia, and that's a company that has research departments in the Netherlands, in Singapore, and in Shanghai. And obviously, I'm from the Netherlands. And we're part of the group Danone. So thank you for joining this session on risk and process. Our first invited speaker is Professor Richard Brereton, and he will talk about the challenges of validating multivariate methods.
Okay, thank you. Can you hear me? Yes, I think the microphones are okay. And thanks to the organisers for inviting me. This is a slightly new type of audience for me. I go to quite a lot of conferences, but I've never been to this statistical conference, this type of conference before. I think it's very nice to listen to the speakers, and since I'm not quite sure of the audience, there will be things here that are very obvious to some people, but are very revolutionary to others. So if I don't quite pitch it at the audience, there'll be discussions at the end of this talk, and there'll also be a round table, and I would say that that round table at the end is probably quite a good time to have a discussion. So this is the topic here. I traditionally regard myself as working in chemometrics, but it's, let's just check if that's okay, it is quite widespread and quite broad, so you don't have to know anything about chemistry or chemometrics to appreciate this lecture. So firstly, I'm going to talk about pattern recognition, and there are many definitions. If you look in the literature, in the 1960s, I did a review recently, it was quite a different definition to nowadays, but most definitions involve classification. It isn't synonymous with classification. It's not just classification and algorithms. It's all sorts of questions that you'd like to ask about the data. For example, is there enough evidence to have the group samples? Are there outliers, unsuspecting subgroups? What are the most diagnostic variables and markers? And the very important one is the method robust in the future. Now, chemometrics in the 70s, 80s, 90s really was very much involved in things like multivariate calibration and PLS. In the last 5 to 10 years, pattern recognition, which has had a very low profile within the not only chemometrics community, the analytical community, food, etc., has started to rear its head because of metabolomics, particularly. And therefore, there are a lot of ideas that are quite important statistical ideas that perhaps not realized or appreciated by practitioners. So I'm going to give you a couple of references. This is a book I wrote a few years ago, Chemometrics for Pattern Recognition, written by Wiley. That's got a lot of the ideas from this lecture. And a couple of recent papers. A paper that was published in 2014, which was on partial least squares discriminant analysis. This is a method that I will be talking about a little bit here. I will tell a lot about the disadvantages of using PLS. We've heard quite a few people using PLS. I think it's a method that is overused there. So that's another which was published about a couple of months ago, which we can see from there. You can just about see the tub. I think you have a web download, which is a review of pattern recognition and how it has evolved over time, how people's perception have evolved over time. Chemometrics was originally called chemical pattern recognition, and then it was taken over for about 20 or 30 years, particularly by people doing calibration and deconvolution, and now people are starting to realize, particularly with metabolomic profiling, the importance of pattern recognition. Right, let's now, people have sort of come in, we've had the introduction, we'll now sort of start on the main part of the lecture. So let's look at validation, and validation might ask how well does a method perform, or is there adequate information in a data set to support a hypothesis? These are quite different questions. We'll see that they're often confused. Traditionally, the very traditional statistical literature contains often known answers. Most people have heard of Fisher's iris data. People know that there are 3 groups, there are 50 samples in each group, there are 3 variables, and we just want an algorithm which tries to divide these groups up. And often the number of samples is vastly greater than the number of variables. So there was for, almost 100 years ago, this was published in the 1930s, R.A. Fisher, and then there were other people like Telling and so on. There's a whole group of people who published certain algorithms that until about the 80s, 70s, 80s were adequate because of the sort of data. Now, we're living in a quite different world, and so we've got to think about it in a different way. So I'm going to talk about some traditional problems, and I'm going to see how things have changed now. So most of the lecture is going through a number of traditional problems. So the title here will be of a set of slides. I'm going to talk about a set of slides here about uncertain hypotheses, and then I'll have another set. So if you get lost on a set, then there'll be a different title. So one of the very important things is we don't know whether the underlying hypothesis is correct or not. As we look at yesterday, we don't know that we can distinguish 2 products, and very importantly is we don't know that the testers, the tasters, have got the biological genes to be able to distinguish 2 products. So we've got product A, product B, and it's a hypothesis we can do. It's a hypothesis that the people in the room are of the right racial, the right genetic background to have the taste buds or the odor receptors to separate it. Now, traditionally, algorithms are benchmarked against known hypotheses, and so you get an algorithm and you say that algorithm can classify 96% and this algorithm 92%, so the 96% one is better. Sometimes people use simulations, but simulations, there is no universal algorithm. They don't always have it. So when we do a classification method, why are we doing it? Now, the traditional Fisher iris data is unambiguous. I just want to get better and better separation because they've got a known benchmark. Now, in the modern day, we don't necessarily have this known benchmark. So often people use test sets. Now, I'm going to talk about a simple method. An auto-predictive model is put everybody together and then try and see if I can separate you. And most classification methods can be mathematically defined as boundary methods, so they put a boundary between 2 classes. And the boundary can be very complicated. In things like support vector machines, it can have individual samples in each group, and it doesn't have to be contiguous. So let's have this hypothesis, and the hypothesis might be, let us look at where somebody sits and let us determine their gender. Are they male or female? I might have that hypothesis, and I can divide around groups here, and sometimes the groups might be a group of 1. Sometimes it might be a whole batch of group. So can I do that, and can I then get an unknown bit of table and find, say, is the person male or female? Now, of course, I can do that, but what am I doing? Am I producing an algorithm to classify people, or am I having a hypothesis that females and males tend to be segregated? Now, I've been to lectures in India and Iran where they really do largely, not completely, segregate the people. You go to a family entertainment and people are not segregated. So my classifier is not entirely, I don't necessarily want to get it correct. My classifier is talking about a hypothesis. So here is a rule. I can set up rules, and there's a rule here, so I won't go through this. You can read that, but here's a rule. I'm going to show you two examples. So here is an example of a traditional audience, and there is a little bit of mixing, but on the whole, the males and the females are separated. So if I use my rule here, the rule I put on the last slide, I will find that 80% are correctly classified. Now, does that mean that if I go to an audience here, the males and females are segregated? It doesn't necessarily mean that. It means I have a hypothesis, and my hypothesis is that there is doing. Now, we're talking about the performance of a classifier. I'm not talking about whether it's the best classifier. I'm talking about that. Let's have a different example. And here is an example where they're more or less mixed randomly. And we'll talk about this. Randomization is not about uniformity. And this is terribly important that we'll talk about later. And a lot of people do get a real problem conceptually here. But we can see that in auto-prediction means put everything together, and test and training sets means have some data that are used to make the model, and the white ones, the ones left out, are the ones that are used to test the model. So I have my rules, and I say, oh, from knowing that, can I predict that? Can I predict that? Can I predict that? And we see about half correctly classified. So for this particular data set, the hypothesis that there is a segregation, it looks like there's a little bit of it, but that's just random. This was done by random number generator. I said we'll move on to that. So what I've done in my classifier is I have not tried to get an optimum best classifier. I've tried to look at a hypothesis. So let's get back onto that. I have my two products, left and right, and I want to see if I can separate them. And the question might be not, can I separate them because they're different, but it might be, can the people who are tasting them or smelling them distinguish them? And it might be that if I get people from Africa and from England and from China who have different genetics or being brought up in a different way, some will distinguish it, some won't. A lot of people don't look at it that way. I was going to ask some questions yesterday, but I thought this isn't not traditional here, but I've worked with biologists who would view it completely differently. So this is a question you ask. Why am I doing this classification thing? Therefore, performance abilities, the ability of a classification algorithm is not necessarily how well is the test, how well is the algorithm. The percent correctly classified could say either things. And that's a very important thing about hypotheses. So there is no easy way out of this. And simulations, people often use simulations, but unfortunately, the simulations would very rarely look at all the problems in real life. And the problem is that you're dealing with real life. You're dealing with humans, for example, that are trying to separate things. You're dealing with products. And there are all sorts of odd things like that. There's mislabeled. There's a person that maybe answered the questionnaire wrong. The questionnaires, if you have complicated questionnaires, people lie a lot and they don't answer it perfectly. And you need one or two of those and in a small sample size, and your whole thing goes wrong. This huge literature comparing classification ability is not very good. So this is a real problem. So there are two ways of slightly overcoming this. And people often don't do this in the literature. The first is to have a null data set, a data set which is just random. And If your classifier gives you 50% or approximately a random answer from this data set, you know it's a robust classifier. So test against the control, but your control is a computational control. The second way you can do it is by permutations, and permutations are quite an important way of doing it. So what you do, and again, I don't see that very often, what you would do is you would permute the people, or you would permute the samples in your case. So you'd have a, can they separate A from B, and you'd randomly move it, and you'd expect no answer. So the answer for this, and we'll get on to some other things, is this problem, is do your background, do your permutation. And I see very few slides and very few people who do it. It's very easy computationally. All you do is just completely randomize the data, randomize things, and do it. Often these are called Monte Carlo methods because you randomize, permute the data lots and lots of times, so you don't have to have a parametric test. You randomize the data, say, 1,000 times, 100 times, and see what answer you have and how your answer fits into that spectrum. So you can get, I don't like p-values, but you can get some percentage probability. So instead of just having your classifier, you can try and look at it against basically the null data set. And a lot of people are scared of doing it, actually, because it sometimes reveals quite a lot about it. Right, so let's have another traditional problem, optimization. Optimization is traditionally confused with validation. A lot of people who use multivariate methods, like principal component analysis, PLS, often ask how many components are there, or support vector machines, what's the most important penalty error or error penalty, or radius for radial basis function. And traditionally people use cross-validation and look at cross-validation error. So you leave samples out, one or a few samples out at a time. You try and optimize the model on those, and you also use it to give an idea of how well the method works. Now, the trouble is left out samples are used to two things, to optimize the model and determine how well it works. That means you've mixed things up. So the way to do that is to separate validation and optimization. Now, the traditional chemometric approaches use things like cross-validation, and often cross-validation has both things in it. And we'll look at ways of separating things in a minute. So so we've done two problems. So the first problem is what is your control? What are you aiming at? Are you aiming at 100% separation, 70%, 60%? What are you aiming at? And the big mistake I think a lot of people in this area make is that they focus too much on the product, the thing in front of them, and too little on the biology behind it. So, and I've seen most things here who don't really look at that. So you tend to look at one side of things, like it's always looking at the Y block and not the X block. But in practice, you're not going to get the perfect answer. And the second is optimization. Let's now look at representative samples. Now, the problem is that a lot of methods are compared. So I have a method A is 92% correctly classified, method B 96%. So let's look at method B. But unless there's a really big difference, now a really big difference might be that, I mean, if I try to separate you into male and female, I can't put straight lines, I can't use a linear method. So it may be that there is a difference there. So unless I look at this, I can't do it. But in many cases, people are looking at percentages. They might look at 5 or 10% difference in performance of two methods. And often these differences might depend on 2, 3, 4 samples out of 100. swapping sides, a slight difference. Now, how do you know that your test set is representative? You might have one outlier in your test set, and you might have one method that's better at outliers. Now, sometimes the one that's better at outliers is worse at dealing with a normally distributed group. You have some methods that are very biased towards outliers. Should you keep that outlier in? What should you do? And you're going to get that. Nothing is homogeneous. You're going to get that. And so how are you going to deal with the fact of unrepresented samples? And how are you going to deal with the fact that if you did a multinormality test on it, if you're going to use methods based on F-tests like Simca and other things, how are you going to deal with the fact that the vast majority of the sort of data that you deal with quite abysmally fails multinormality? The number of people that test for multinormality before they then use statistics to assume it is quite low. So to overcome this, what you would do is you would generate all the subsets many times. So what you do is you go many, many times over and generate the subsets. So you don't just have one test set and you don't have one training set. And we heard yesterday about the bootstrap. The bootstrap is sort of a way of doing this, which is good. But use that for optimization and have another level there using it for the test set. So you want to regenerate the test set and you want to regenerate the optimization set. Hopefully not everybody will walk out, but we'll want to regenerate the test set and we want to regenerate the optimization set many, 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 many times over and do both, not just do one of them. And a way to do it might be that you can maybe just see that there. So here is your full data set. I divide it into test and training set, and I divide it 100 times over. So each sample, if I did a third in the test set and 2/3 in the training set, each sample, if it's 100 times over, on the whole would be about 33 times in the test set, and in 67 times in the training set, and do a bootstrap, which we heard about yesterday, and that is a slightly different way of dividing the data out, and do 200 bootstraps. So that typical approach will involve 20,000 iterations. So I've got modern computers. If you look at something like Moore's law, modern computers are very, very very intense. They're very, compared to what happens in Moore's law. If you looked at Moore's law, the computing power doubled every year. It's going to increase 1 million times in 20 years per unit cost. Well, I think it's doubling every 18 years now. That would still be 1 million times faster in 30 years. Now, cross-validation, when was it first used? 30 years ago. So why should we use that? So what you do is you do very iteratively intense methods to get an average. Not just the cross-validation, but also test and training set. That means unrepresented samples are averaged out. Right, now I'm going on to another variable selection. So I've talked about some problems. I'm going to talk about a very simple example of tossing a coin 10 times. Now, if this is an unbiased coin, I toss it 10 times, and you see that sometimes I'll have 8 or 9 heads. So that most people understand that, binomial theorem, fairly straightforward statistics. So let's do that. If I then repeat this 1,000 times, I will get several cases of 8 or more heads. That is randomness. That's what I expect. I'm not going to expect 5 heads every time. So what I could do is I could select those tosses of coin that give 8 or more heads. These will be approximately 45 for an unbiased coin, plus or minus a bit. And I could form my model with those 45 things, which people could say are the best markers. They're the best marker compounds. I've seen biologists do it hundreds of times over. They've said we've got 1,000 marker compounds. We're going to look at the 45 best marker compounds. We're going to look at the best marker compounds. Then we're going to form a model, and we get perfect classification. Of course, we would then incorrectly conclude that the coin is biased. Now, this is something like PLSDA does this very well. It looks at the variables that have the biggest correlation with, say, the classifier. And if there are thousands of variables, then the variable sample ratios are large in PLSDA, then we can then form very good models, and there are even more sophisticated methods of being published, etc., and used, which, from total rubbish, totally unbiased. I've got my unbiased coin, and it looks biased. So here is an example from a recent paper I gave you. The left-hand side is the PCA scores plot of the first two PCs, and using training set auto prediction, of course, we'll get on to the problems of doing this test set. On the right-hand side are the first two PLS components. So the right-hand side, I've got this random data set, and if I look on the right-hand side, it looks as if they are perfectly separated. But I've told you the principle. The principle is, and PLS does this very well. So people like PLS because it does it very well. What you've got to understand is randomness is not uniformity. So the top sequence is not random. A typical random sequence might be the next sequence. So there's always some clumping. So a clever algorithm looks at its clumping, uses that clumping to form a model that apparently is successful. And that is a problem that a lot of people find. I mean, I've had projects and I've shown PLS scores plots to sort of biologists and shown them PLS plots. What should we publish? Oh, we like that PLS scores plot. We'll get a paper in PLOS One. We'll get a paper in Nature. We'll get a paper there. And I say, yeah, you might do. I mean, I've said this thing about I can get random data and get any separation you like. So I've said that if you want a successful grant application, you don't want no separation. You don't want perfect separation. Perfect separation, the problem's solved. No separation, the problem's insoluble. So you want a separation about like that, then you'll get your grant application, then move it around, and so you can keep about 4 years, 5 years, just moving it around and separating it out. And the grant committee, the senior managers, won't know any difference because you might put technically how you did it at the bottom. But a lot of people do that, unfortunately. So variable selection is important, and people say, let's get rid of noisy variables and do it. But unfortunately, the traditional thing that in spectroscopy, chromatography, you get rubbish variables out. Variables are not going to correlate with your prejudice. So they take it out, and this is over-optimistic, and you can then get this over-optimistic prediction because you have used the prejudice to remove, and yet, if you have these thousands or tens of thousands of variables, that will distort the message. You might be looking at genes. There might be only 10 genes that are of any use. So if you had 10,000 genes and weighted them equally, you'll get nothing. So let's reduce it down to the ones that we're doing. But how do you know those 10,000 genes aren't due to some random chance? Unless you've got a large number of samples, you will always get that. You will almost always find that. So how to avoid this? Well, select variables only on the training set. Now, the dilemma is that, as I told you earlier, you need to make thousands of different training sets. So each time you take samples out for a training set, you are selecting different variables. And not only that, you're going to have different means, different standard deviations, different number of PLS, PCA components, because each time you do your training set, there's going to be a different variable selection process. So this is a bit of a dilemma, and there's no universal solution, but you can select variables in a consensus way. So you could make 100 training sets, and then in each training set, which variables are selected the most times, so they're probably going to be the better variables. If you had variables coming out almost randomly, you know there's nothing, but if you did it, remember it can be a serious problem if you've got thousands of variables, and you've got a serious problem, only a few are significant, the rest are noise. The trouble is, are those few significant of any meaning at all, or did they turn out randomly? But you can do it. Now, but aware that selection and weighting variables can result in over-optimistic models, and particularly methods like PLSDA, which are meant to find these best variables. So they look for it in the top components. So be careful about it, but you can get over it. But these are things that you can overcome. But obviously, a lot of your results will look less positive if you do it. And you've got to understand that the variables you select, which may be your marker compounds, the important things, may be less certain. But sometimes you will get a needle out of a haystack. So the final thing is comparison of methods. There's a large and very misleading literature here. This goes back years when you had traditional benchmarks. People, in order to justify their grant or paper or presentation, will say, I've got a new method. Well, have we now got to the infinitely best method that will work on infinitely best thing ever? People like publishing new methods because it gets them papers, it gets them citations, it gets them things like that. They love it, and it's interesting, and people should. It's just that they're then forced often by editors and referees to show that their method is better. Well, you can always find a test set or data set doing it in some way in which your method is better than others. It doesn't really mean anything. It doesn't mean the method shouldn't be reported or used, but the claim isn't there. And there's a strong pressure. People say, well, we've given you so much for 3 years, 4 years to get a PhD. You've come out with a method, and you can't say it's better than any other method. So in order to justify it, get through your grant, get through your PhD, you do this, and there are ever more esoteric claims in the literature. So you've got to be aware of this. It's often not possible to compare methods directly. Here's an example that I use a lot, classification. The left is a one-class classifier. A one-class classifier puts a boundary around data between class. So I could just have a one-class classifier for the blue group, or I could have for the red group, or for both. Whereas a two-class classifier puts a boundary between. So partial least squares discriminant analysis puts it between, Simca puts it around. Not that anybody uses Simca much now, but they used to, but support vector data description, quadratic discriminant analysis, etc. The trouble is that I have different types of verdicts. So for example, if I have a two-class classifier, a contingency table has just got these things. I've got about 5 minutes, so I'm going to go quite quickly through the end of this. And the one-class classifier has lots of different verdicts. I can't compare these. So I can't say, oh, Simca works better than PLSDA, or vice versa, because they're not comparable. They're just simply not comparable. The other thing, very important, is pre-processing can radically change a method. A partial least squares discriminant analysis can be exactly the same as linear discriminant analysis if all significant components are used. So if only one component is the same as Euclidean distance centroid. Now, I prefer these statistical methods because they have specific statistical properties, whereas PLSDA doesn't. It's just an algorithm. Whereas LGA, I can talk about the variances, and we won't go into that. I can talk about fundamental things about the data. But the problem is, a person says, I use PLSDA. I said, well, how many components? What pre-processing did you do? Oh, I use this. Well, you could have used LDA, a linear discriminant analysis. That's a Fisher thing known 100 years ago. Same answer, exactly the same answer. Or, no, I didn't do that. And so I think that the very key thing is that people say, I use method A and I use method B. And I say, well, no, method A is incomprehensible without all the steps described. And those steps could be more important than the algorithm. So I say something like PLSDA, it's like, I used addition, I used multiplication, I used this, and it's fair enough. I'm not unhappy that you used it. I'm perfectly happy. But so there is too much of, I use this algorithm, I use that algorithm, and too little of, here are the data preparation steps. So in PLSDA, there are so many choices of parameters. There are about half a dozen key choices. These are probably more significant than the algorithm in the middle. And people have a real problem with this because they like to say, I use this and sophisticated algorithm. I say, yes, I like to use addition. I use multiplication. It's a bit more than that, but that's all it is. The choice of parameters is terribly significant. And you can mathematically show things like PLSDA are exactly the same as other statistical techniques under certain circumstances. This has been in the literature for years. I mean, etc. So they're exactly the same. They're not different. But in other circumstances, they are. So if you don't tell us these things, what can you do? So how to view this? So I'd view a classifier as one step in a series and a useful step, but the other steps you should focus on, and people often don't because it's uninteresting. It's not interesting to say, some people do write papers on centering and on etc. Lots of ways of determining number of components. They write it on that, but we do it. But it's not so interesting. It's more interesting to say I used a sophisticated algorithm. So it's often unwise to compare different approaches directly, and some can't, some physically can. What I would say is the pragmatic approach is just to use several core independent methods and then look at a consensus of it. And some people do use consensus methods. Okay, so I'll finish this lecture now. So here is a conclusion. I've gone through a lot of things. I just actually took a miscellaneous thing. I could have many more things I could put in, much more detail. And I'm talking mainly about classification because that's my main expertise. Originally, it was a very simple thing. It was quite straightforward with known answers. The variables were much smaller. A lot of the original data, right up to about 70s, 80s, focused on algorithms. And both methods were quite straightforward. There were less decisions down the road. Now, modern approaches are much more complex. But as there is more data, you get better computer power. So the simple sort of Fisher linear discriminant analysis with maybe cross-validation, blah, 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 of 50 years ago was fine because the data sets were quite simple. There wasn't this huge amount of data around, huge number of variables. It was quite simple. People were interested in quite simple problems. As the data gets more complicated, you can do this 20,000 iterations. You can do it, and 20,000 iterations would take less time than one iteration 30, 20 years ago. So So change it. And I think that in the literature, there's far too much emphasis on algorithms. People do that because it is more exciting, it is more interesting, it gets lots more papers and lots more grants, and it's good to say you've got a new algorithm, but there is not always that much focus on basics. So this lecture's been just a very big tour of a number of problems that I come across all the time, and I've come across, I write papers, books in this area, and it's a bit sort of trying to move these methods, pattern recognition methods, in sort of applied science into the modern world with some of the problems that we have. And to some people in this audience, this will be straightforward. I'm sure there are people who will say, yes, I do this, I'm an expert enough. To other people, it'll be quite new, and I would just say watch out. And I wouldn't say don't use these methods. These methods are very important, increasing importance, but you're in a new world here. You've got new problems and new difficulties, and really that's all I'm trying to express. But I was asked to talk about validation in this lecture, so this is what I've talked about. Okay, thank you very much.
Okay, thank you, Professor, for this very strong and convincing plea. Any questions from the audience?
So I have the feeling that most of your the issues and the points that you mentioned for pattern recognition, I have the feeling that most of them they should be applied for quantitative modeling. Do you agree, or what is the difference for you?
Well, I mean, my lecture is mainly on, obviously on qualitative, well, stuff, but I would say quite certainly things like test and training set things and comparing of methods you can look at for quantitative modeling. For example, calibration, are you going to use support vector regression, are you going to use PLS, are you going to compare them, how are you going to prepare the data? I mean, I'm not so much an expert on something like calibration, but I would say that quite a lot, some of them like these permuting data, even so, I would say probably would be fairly meaningless in quantitative modeling, but other things like variable selection and method comparison, yeah, I mean, yeah.
Anybody else? Maybe not a question, but an example. Oh.
Thank you for your presentation. Concerning algorithms, what do you think of bagging techniques in machine learning, where we try to aggregate several classifiers, for example? You say it's difficult to compare, depending, there is not the method, but in bagging, in fact, you take advantage of several classifiers, several techniques.
Yes, some people use consensus methods. I mean, the majority vote methods, etc. And in some cases, I mean, there's still going to be the problems of finding the right test set and finding the variable selection. But I mean, there are consensus methods that are used in machine learning and majority vote methods to decide what the answer is. So that they're used. I mean, I said I still think people do have problems of the sort of training test set things and variable selection, which are not always overcome, but I certainly it is done in machine learning, and I think that's fair enough. I wouldn't go against that. Is that what you want? I mean,
yeah, it's often the problem of the number of rows on the
yes.
most application in machine learning, you don't care about it's a good key because you've got a lot of rows. So test sets and so on, it's not a problem for them. When you look at metabolomics data, it's a real problem in validation because you can't.
Well,
you
sometimes
can't define
you can.
a test set. There is so few rows.
Yes, that's a serious, but that's a serious problem. Whatever method you can use, machine learning or not. I mean, there is a method that what you're looking for, you just haven't got the data there, and it's getting more and more serious. I mean, if you have sort of 50 samples and 1,000 variables, I mean, it doesn't matter what method you use. But the problem is that people can only really know that by doing a lot of these null methods, and I mean, often you have to. The trouble is, people do have very expensive projects, and particularly human metabolomics, where they can only get 100 clinical samples, and that's cost them $100,000, and they've got to get something out of it. And you've then got to tell people, well, I'm afraid it's impossible. You need 10,000 people. I mean, your genetic pool is wrong, your thing. But what can you do? A lot of people sort of fiddle it and show sort of results that might support a hypothesis, but don't show anything very fancy. A lot of people use statistical stuff, but if you can't get the data, all you've got to report is, I mean, that it's consistent with an idea, but you've got to go on and do another experiment. And then they'd say, well, we spent $100,000 or whatever on this. We've got 100 people. We've done that was the best we can. We went to hospital and we took these people out. And then you've got to say, well, look, we don't do it. You need 10,000 people. And then it's up to the sponsor if it's important enough to go and do it. I mean, I don't know what else you could do, but that is a very common problem. And a lot of people do not like the rigid validation of methods because it often tells you that you can't say anything from that. But I mean, many people, unless you use it as I mean, I've been expensive projects, and I say, well, I just treat that project as a pilot study. It's worth going on, but the sponsor will want to do this and that, and they get into a lot of trouble. I mean, in metabolomics, there's serious trouble in that, and very little has actually come out from it. But anyway, that's just a personal view.